Hello all, a very good day to all of you. In this session, we will discuss all the questions that have come from analog circuits in 2017 set 2 GATE examination for electronics and telecommunication branch. Okay. So in 2017, right, there are 7 questions. So 4 are of 1 mark and 3 are of 2 marks. So 11 marks have been asked from this subject in 2017 set 2. Okay, so let us discuss all the question one by one. So the first question is an easy one, right? The output voltage V0 of the diode circuit shown in the figure is connected to an averaging DC voltmeter. Okay, so at the averaging DC voltmeter, we know measures the DC or average voltage of the waveform, right, across the voltmeter, right? So we have to find out the reading of the voltmeter, neglecting the voltage drop across the diode. So we know the input is a sine wave, right? It is having positive and negative half cycles like this. This is equal to 10 volt. Okay. During the positive half cycle, the diode will be forward bias and it will behave like a short circuit because it is saying you have to neglect the voltage drop. So whatever input we are applying, right, that will come to the output. Fine. So my V output will be completely come to 10 volt, right? This is 10 volt. Okay. So during positive half cycle, since diode will behave like a short circuit, complete V input will come to my V output. So the waveform will be like this. During negative half cycle, right, the diode will be reverse bias. So it will behave like a open circuit. So my output should be 0. Again during positive half cycle, again my diode will be forward bias. Again my output will be the input, right? So it will continue. So I got at the output a half wave rectified sine wave, right? And we know the average voltage of half wave rectified sine wave is the maximum amplitude of the wave Vm by pi. In this case, the amplitude is 10 volt divided by pi. What is the answer? 10 divided by pi, 3.18. So answer should be 3.18 volt. It's a easy one. Second question. In the figure, D1 is a real PN junction diode, right, with a drop of 0.7 volt under forward bias. Okay, and D2 is a general diode with a breakdown voltage of minus 6.8 volt. Okay, means if we impress a reverse bias voltage of 6.8 volt or more, the general will be regulated at 6.8 volt. Okay, the input is a periodic wave as shown in the figure, right? What it is asking, assuming 10 tau, tau is nothing but the time constant of the RC circuit, right? Tau is nothing but R into C. Assuming 10 tau is very less than the time period here, what is the meaning of this is, if we apply input voltage, since my time constant for charging and discharging is very small compared to the time period, so it will charge instantly or discharge instantaneously, because since my charging time constant and discharging time constant is very small compared to the time period, the meaning is the capacitor will charge quickly and discharge also quickly. This is the meaning of this assumption. Okay, tau is the time constant of the circuit, right? Find maximum and minimum value of the output waveform in this circuit. Okay, so you see, when you apply during positive cycle, okay, positive cycle, right, V in is equal to 14 volt, right? So initially the capacitor might be uncharged. So when you apply 14 volt, right, the capacitor will charge and the and some positive voltage also I will get at the output. The instant I apply 14 volt, right, since it will charge quickly, and also the output here, right, when I apply positive bias, this will be forward bias, D1 will be forward and D2 will be reverse. So when D1 will be forward bias, we know the drop will be maximum 0.7, and when it will be reverse bias, the maximum here will be 6.8 volt. So the output, if we apply 14 volt, the output cannot go more than D1 plus D2 voltage drop. So it will be equal to 0.7 plus 6.8 volt is equal to 7.5 volt, right? So during the positive half cycle, when I apply 14 volt, instantaneously my capacitor will charge to my input minus output. So my VC will be 14 minus my output voltage will be 7.5 volt will be equal to 6.5 volt. So it will be 6.5. So if the diodes would not have been there, then my capacitor would be charging to 14 volt the input. Since the output voltage cannot go beyond 7.5 volt, or it is restricting my output to 7.5 volt, that's why my capacitor will charge to 14 minus 7.5. If this would not have been there, the constraint of output going to 7.5 volt would not have been there, then my capacitor would be charging to input completely to 14 volt. But because of the constraint of the output, my capacitor cannot charge beyond 6.5 volt. Okay, this is clear. So during positive half cycle, my output will be 7.5 volt. Is your V output during positive half cycle. Okay, then you see at the end of my positive half cycle, my capacitor have been charged to 6.5 volt. Okay, so with this information, we'll go to the negative half cycle. So till this point, what is there? So here I have the charging of the capacitor of 6.5 volt, right? The instant I have gone to minus 14, right? When I apply V is equal to minus 14, right? What it will do at the output, what I got at the instant of t by 2, at t by 2, t is equal to t by 2 plus, means just after t by 2. What is the V in? V in will be equal to minus 14 volt, right? When V in is minus 14 volt, the capacitor is already charged to 6.5 volt. What will be my output at that time? My V out will be, if you see 14 minus 6, right? Plus or minus 14, minus 14 plus or minus 6.5 will be minus 6.5 will be equal to 20.5 volt at the instant t by 2 plus. Okay, then what will happen? Since minus 20.5 volt is coming at t by 2, so D1 will be reverse bias. So it will behave like almost like a open circuit. And D2 will be forward bias, so it will be like a short circuit. So effectively, since it is open circuit, this is effectively don't come into the picture. So in reverse bias, what will happen? This is my R and this is open. Okay, because our D1 is reverse bias and I am applying a voltage of minus 14 volt, or I can say 14 volt here, because this is minus, this is positive, this is plus 6.5, this is minus 6.5, V0, this is at time t is equal to t by 2 plus. Okay, this is the circuit just at the instant of t by 2 plus. Okay, so my output at that particular instant is 6.5 plus 14 is equal to minus 20.5. Okay, now what will happen? The capacitor will charge, or you can say the other way, it will discharge in this way, right? Or I can say it will charge towards the negative 14 volt. Okay, so at time it is equal to some significant time. What will happen? Since my RC is very small compared to my time period. So this capacitor will charge instantly to minus 14. Okay, so after some time, the capacitor voltage will changing from 6.5 volt to minus 14 because it will charge to the input voltage through this resistance R. Okay, so if I want to draw the output, right, this is my input, this is my input. If I want to draw the my output here, this is plus 14, this is minus 14. During positive half cycle, my output is constant at 7.5, constrained by these two diode, it will be 7.5. Then at T by 2 plus, my output will have gone to minus 20.5. Right now, my capacitor will slowly discharge, then charge to minus 14. Okay, so when it will charge to minus 14, what will be my output? My output will be from here to here minus 14, here to here plus 14. So it will be 0. Right. So you see, when my capacitor will charge to minus 14 like this. Okay, this is positive, this is negative. Okay, what is my output? Output will be plus to minus 14, again minus to plus 14. So output will be V0 is equal to minus 14 plus 14 will be equal to 0. So when my capacitor will charge from 6.5 volt to minus 14 volt, my output will be 0. So quickly my output will be 0. Right, and since my RC is very small, so my capacitor will charge to minus 14 quickly, so my output will go to 0. The time my capacitor will charge to 14, the time my capacitor will charge to 14 volt, you see my output will be minus 14 plus 14 will be equal to 0. Okay, initially my capacitor voltage was 6.5, that's why my output was minus 20.5. Then my capacitor voltage have gone from 6.5 to minus 14, at that time my output become 0. Okay, so the maximum negative voltage will be minus 20.5 just after T by 2 plus. Okay, so the answer should be 7.5 and minus 20.5 is given. Yeah, this is the option A. Okay, let's go to the next question. Consider the circuit shown in the figure. Assume base to emitter voltage VB is equal to 0.8 volt and common base current gain alpha of the transistor is unity. Okay, what is common base current gain? Equal to IC, base is common, right? The output current is collector and the input current is emitter. Okay, so common current gain will be equal to the output current is IC, the input is IE, because the base is common. Okay, so this implies IC is equal to alpha into IE, but since alpha is equal to given unity, so is equal to IE. So when IC is equal to IE, I can say my IB is equal to 0. So means IB is very small, it cannot be 0. So you can assume to be 0. Okay, it's extremely small. So the collector current is equal to emitter current. This is the assumption of this current gain alpha is being to unity. Right. So this is the first assumption. Okay. Now, what it is asking, the value of collector to emitter voltage. This is collector, this is emitter, this is base. VC is the collector to emitter voltage. So for that, it's an easy question, right? What is the base voltage? Base voltage is equal to VB is equal to, okay, 18 into 16K divided by 44K plus 16K. So how much? Is equal to 18 into 16 divided by 44 plus 16. I got 4.8 volt. 4.8 volt. Now what is VE? VE is equal to VB minus VB minus VB. So 4.8 minus VB is given 0.8 is equal to how much? 4 volt, right? So VE is equal to 4 volt. Then what is IE? I is equal to V by 2K. 2K is equal to 4 volt by 2K is equal to 2 milliampere. Right? And I is equal to 2 milliampere. What is IC? IC is also equal to 2 milliampere because IC is equal to IE. Okay. Now let us see this question. Okay. IC is equal to 2 milliampere. IE is equal to 2 milliampere. Right? Both are 2 milliampere. So let us put a KVL in this loop. Okay. So 18 minus IC into 4K minus this is VC minus IE into 2K is equal to 0. So this implies VC is equal to 18 minus IC is nothing but 2 milliampere into 4K minus IE is 2 milliampere into 2K. So is equal to 18 minus 4 into 2, 8 volt minus 2 into 2, 4 volt. 4 volt is equal to 18 minus 8 minus 4. 18 minus 12 is equal to 18 minus 12 is 6 volt. Okay. So answer should be 6 volt. 6 volt. Okay. It is a easy question. We see. So and since IB is almost 0, I neglected the base current. Okay. So this is another question. Okay. In the circuit shown in the figure, P and Q are the input, Y is the output. Okay. So what is the logic implemented by the circuit? Okay. So we know my PMOS will be on when my input will be 0 and NMOS will be on, my input will be 1. Right. So let's see. Suppose take the case when P is equal to high. When P is equal to high, this is 1. Right. When this is equal to 1, right, the PMOS will be off, right? Because when I apply P is equal to 1, right, PMOS will be off because for PMOS to be on, I have to apply 0 here, right? So PMOS is off. When P is equal to 1, what is NMOS? NMOS is equal to on, right? NMOS is on. So when NMOS is on, okay, what is Y? Y is nothing but here is Q bar, right? Whatever this is Q means this is Q bar. When NMOS is on, whatever at the source it will go to the output. So my output will be equal to Q bar, right? So when PMOS is off, NMOS is on. On means this is almost behave like a short circuit. So whatever in the source will go to the output will be equal to Q bar. Okay. So next case, consider the case when P is equal to 0. So when P is equal to 0, right? When P is equal to 0, okay, NMOS will be off, right? NMOS is equal to off. And what is PMOS? PMOS will be on, right? So when NMOS is off means this is totally gone. What is PMOS? PMOS will be on. On means whatever is the source it will come to my output. At source what is there? Q is there, right? Here it is Q. So my Y will be Q because when P is equal to 0, PMOS will be on. And PMOS will be on. Whatever is there at the source will come to my drain of PMOS or nothing but my output. So whatever, so at the source it is there is Q. So Q will come to my output. So Y is equal to Q. So with this information, so we have to solve the circuit. So now P, Q and output Y. Okay. So P can be 0, 0, 0, 1, 1, 0, 1, 1. Okay. When P is equal to 0, when P is equal to 0, output Y is equal to Q. Q means directly come, 0 will come. When P is equal to 0, again output is Q. Q means 1 will come here. When P is equal to 1, output is equal to Q bar. Q Q bar means 0 bar means 1, and again P is equal to 1, output is Q bar means again 0. Okay, so we can say my output will be high only when either of the input is high. Okay, either P will be high, Q will be 0, or Q will be high, P will be 0. Then this will be, is a standard XOR circuit, right? So the output should be B. Answer should be B. Okay. Let us go to the next question. So this is an interesting question, right? Looking simple, but it's little bit interesting. Okay. Assuming that transistor M1 and M2 are identical. Okay, both are same, I can say, and having a threshold voltage of VTH of 1 volt. The state of the transistor, I have to find out whether M2 and M1, which transistor is in which region. Okay, so we have to figure out the transistor M2 in which region and the transistor M1 in which region, right? So the first and foremost thing, you put all the information that we know. Okay, for a transistor to be in saturation, we know VGS minus VTH should be less than equal to VDS. So I can say, in the other way I can say, so for transistor to be in saturation, the condition is VGS, VDS should be greater than equal to VGS minus VTH, and VGS is greater than VTH. That is definitely to make the transistor on. So this is the important condition. So when a transistor is called linear region is when my VDS is less than VGS minus VTH. Right? This is the important condition for linear. Okay. This information we know. And also, what else you know? For transistor M2, right? VG2 this is G2. This is drain 2. Okay. This is source 2. This is source 2. This is drain 1. This is source 1. This is gate 1. Clear? So for M2, VG2 is equal to 2.5 volt and VD2 is equal to 3 volt. Right? We know the condition. We have to check the condition for saturation. For saturation, VDS2 should be greater than equal to VGS2 minus VTH. Okay, so VGS2 is nothing but VD2 minus VS2 should be greater than equal to VG2 minus VS2 minus VTH. So VS2 got cancel. So I can say this M2 will be in saturation if VD2 is greater than equal to VG2 minus VTH. Okay, so now you see VD2 is equal to 3 volt, VG2 minus VTH is equal to 2.5 minus 1 is equal to 1.5 volt. 1.5 volt, right? So VD2 is nothing but 3 volt. VG2 minus VTH is 1.5 volt. So the condition is satisfied, right? So I can say undoubtedly my M2 will be in saturation. Okay, because for M2 I could understand that VD2 is greater than VG2 minus VTH, means VD2 is 3 volt, VG2 minus VTH is 1.5 volt. So M2 is in saturation. Now M2 is saturation we know. Okay, for M1, okay, for M1, how to know? For M1 I know VG1, right? VG1 or VGS1, right? VGS1, because source is grounded, so I can say VGS1 is equal to 2 volt. But I don't know the drain voltage, VDS1. VDS1 is I don't know. Okay, then how to decide whether transistor M1 in saturation or linear? Because for knowing the condition I have to know the VDS also, right? But I know VGS1 only. So let us assume. So you can assume something. Then we check the assumption. Let us assume that M1 is in saturation. I take a assumption. Then you will have to verify the assumption also. Okay. So thing is M2 is already saturation, that is confirmed from the circuit condition, but M1 is not confirmed. So because I don't know VDS1, so we have taken an assumption M1 is in saturation. Okay. Then you have to verify whether it is true or false. Okay. You see, since M1 and M2 are connected in series, the current in M1, the IDS of transistor 1 equal to the IDS of transistor 2, since the same current will flow through M2 and M1. Okay. So IDS1 is proportional to VGS1 minus VTH the whole square, because transistors are identical. So mu1 COX double by L is same for M2 and M1. So it is proportional to VGS minus VTH, neglecting the channel length modulation. Similarly, IDS2, okay, proportional to VGS2 minus VTH whole square, right? Since the currents are equal, definitely VGS1 minus VTH should be equal to VGS2 minus VTH. Then only my currents can be equal, because current is directly depending upon VGS1 minus VTH and VGS2 minus VTH. The current can be same only when these two are same. Okay, so this implies VGS1 minus VTH should be equal to VGS2 minus VTH in order to ensure that transistor M1 and M2 are saturation and the same current is flowing. Okay, so VTH get cancelled. This implies VGS1 is equal to VGS2. Okay, what is VGS1? It's 2 volt, right? 2 volt. So 2 volt is equal to, what is VGS2? VGS2 is equal VG2 minus VS2 equal to, what is VG2? VG2 is nothing but 2.5 volt minus VS2. Source 2 is drain 1 is equal to VDS1, right? Minus VDS1. Because S2 is nothing but drain 1. So I can say VDS1 is equal to VS2. Okay. So what is VDS1? VDS1 is equal to 2.5 minus 2 volt is equal to 0.5 volt. Okay. What is VGS1 minus VTH1? VGS1 minus VTH equal to how much? 2 volt minus 1 volt. 2 minus 1 is equal to 1 volt. So we have assumed that transistor M1 is in saturation. So the condition should be VDS1 should be greater than or equal to VGS1 minus VTH. Here VDS1 is 0.5 volt and VGS minus VTH is 1 volt. So the condition of saturation, right, is not meeting, because VDS is not greater than VGS minus VTH for transistor M1, because it is 0.5 volt, it is 1 volt. So the condition is not meeting. So it is not in saturation. So the assumption of saturation is wrong. So definitely it is in linear, because we assumed in saturation, then we find out the voltage of the VDS1, then we check the condition is not meeting. So the transistor M1 is in linear region. Okay, so M1 is in linear and M2 is in saturation. So what is the condition that? So state of M1 and M2. M1 is in linear, and M2 is saturation. So answer should be C. Okay. Let us go to the next question. In the circuit shown, transistor Q1 and Q2 are biased, okay, at a collector current of 2.6 milliampere. Okay. Assuming that the transistor current gains are sufficiently large so that the collector current equal to emitter current. Okay. So what it is meaning? IC1 is equal to IC2 is equal to 2.6 milliampere. Okay, and beta is very high, very high. So alpha is equal to near to alpha is nothing but beta by beta plus 1 near to equal to 1. So IC is equal to alpha into IE. So approximately IC is equal to simplifies IC approximately equal to IE. Okay, because since beta is large, the current IB is very small. So IC is equal to IE. Okay, this is also given. And also given the thermal voltage is 26 millivolt. Then we have to find out the magnitude of voltage gain in the midband frequency range. Okay, so actually this is a very easy question. Okay, so we have to solve it within 10 seconds. Okay, so let me tell you that approach of 10 seconds, then I will explain you in detail. Okay, so how to solve it in 10 seconds? You see, so for solving in 10 seconds, we need some I can say insight of the circuit operation, or you should have some practice on the analog circuit. So if somebody would have been practice so much lot of circuits, then he can solve in 10 seconds. So the thing is, you see, since IC is given, okay, means already a DC bias condition is given. DC bias is 2.6 milliampere. Okay, and you see the resistance looking to the transistor Q2 is 1 by GM2. Okay, so whenever we look to the emitter, the resistance is 1 by GM2. Okay, so what is the current here? The current here is nothing but Vs by 1 by GM1, because the resistance here is 1 by GM1 and below is 1 by GM2 plus 1 by GM2 is the current. The current flowing through the resistor 1K. So RC is the output voltage V0. Okay, so V0 is equal to minus Vs into 1K divided by 1 by GM1 plus 1 by GM2. Since IC1 is equal to IC2, so GM1 is equal to GM2, because GM1 is equal to GM2 is equal to IC by VT, we know. So it will equal to 2 by GM1. So I can say minus Vs into GM1 by 2 into 1K is the output voltage. So gain will be V0 by Vs minus GM1 by 2 into 1K. Okay, this is very straightforward answer in 10 seconds. For that, we have to know the resistance looking to the emitter is 1 by GM2 and the current in the collector, nothing but the small signal current. Okay, this is nothing but current. This is nothing but my small signal current is IC, is this one, and it is flowing through my resistor R1K, developing the output voltage V0. Okay, and since it is assuming that midband frequency, so we need not to take any capacitor into account. Okay, so how to solve in detail I will give you. Okay, we know first thing is you have to know the resistance looking to the emitter, looking to the emitter of Q2 is how much. Okay, so that we want to see. Resistance looking is how much, you see. For that, this is a transistor. Okay, in order to find the small signal resistance, I have to sort all the DC, right? So the DC voltage is sorted, right? And base also is sorted. Since RB is connected between two ground, it is of no use. Okay, so in order to find the small signal resistance to the emitter, what you have to do? You have to apply a voltage source Vs and find the current source. If you apply a voltage source Vs and find the current out of the voltage source Vs, then the resistance should be Re looking to the emitter of transistor 2, Re2 is equal to Vs by Is. Okay, so how to do that? For that, you replace the circuit with its equivalent, small signal equivalent. Okay, so for finding the Vs by Is, I will replace the BJT by its small signal equivalent circuit. Okay, so there is a base B2. Okay, then I have a emitter E2, right? Between base and emitter, the resistance is R pi. So this is the small signal equivalent circuit, and we know R pi is equal to Vt by the DC current beta, DC current by DC base current, right? R pi is the Vt thermal voltage by DC base current. Since DC base current is negligibly small, okay, so I can say R pi is infinity, so it will be like a open circuit. So this will be like a open circuit. Okay, and between collector and emitter, I have a small signal current. Okay, current is equal to GM2, because I am looking up the transistor 2 into VB2, right? And my collector here is grounded. Collector here is grounded. This is collector, is grounded. This is collector, is grounded. Between emitter and ground, I have the voltage source Vs. Then I have to find out the current coming out of the source Is. Okay, and base B2 is connected to the ground. Okay, very easy one now. Now, if I can find out Is, I can calculate Re2. Okay, so let's do that. First thing is, what is GM2 into VBE2? VE2 is, okay, is nothing but my source Vs. VB2 is equal to how much? Is 0. So VBE2 is equal to 0 minus Vs is minus Vs. Okay. Now we put a nodal here. Current coming in is minus Is. Again, there is another current coming in is minus GM2 into VB2 is equal to 0. This implies Is is equal to minus GM2 into VB2. Okay, we know VB2 is minus Vs, so minus GM2 into minus Vs is equal to GM2 into Vs is the current coming out of the source. Okay, so this implies my Re2 is the small signal resistance looking into the emitter of transistor Q2 is equal to Vs by Is is equal to 1 by GM2, which I directly put here 1 by GM2, right? So now we know the resistance looking down is 1 by GM2. Then we have to do the small signal equivalent circuit. So when I am doing the small signal equivalent circuit, I have to replace all the DC to ground, because I am only interested in the AC signals, right? So this is I put to ground. Okay, then this transistor is Q1. Then from this emitter to this whole Q2, I can replace by resistance called 1 by GM2, right? Because here I have seen the resistance looking is 1 by GM2, and base to ground I have a source Vs. Okay, Vs. This is 1K. This is my output V0. Okay. So now again we have to draw the small signal equivalent circuit of Q1. So in this case, so you remember, whenever there is a resistance at the emitter, we will apply the not the hybrid pi model. We will apply the T model. T model says this is base B1. From B1, then I have a resistance called 1 by GM1. This is my emitter E1, right? And from emitter E1 to ground, I have resistance 1 by GM2, right? And at the collector to emitter, this is my collector. The current is equal to, we know, GM1 into VB1. Okay, this, and from V base to base to ground, I have the input source Vs. Okay, and from collector to ground, I have resistance that is 1K, and this is my output V0. Correct? Now, what is my V0? V0 is equal to minus GM1 into V1 is the current into 1K minus GM1 into VB1 into 1K is the resistance of the collector. Okay, first see the equivalent model between base and emitter. I am a resistance 1 by GM1, right? Between emitter to ground, I have resistance 1 by GM2. The source is connected between base and ground, and collector to emitter, I have a current GM1 VB1, right? Then from collector to ground, I have resistance 1K. Okay, so this is equal to minus GM1 into what is VB1? VB1 is nothing but, if you see, this is base, this is emitter, nothing but Vs, okay, into 1 by GM1 divided by 1 by GM1 plus 1 by GM2. Simple resistor divider, right? This is Vs is between here and ground. I want to know the voltage base to emitter. That means Vs into 1 by GM1 by 1 by G1 plus 1 by GM2. Simple resistor divider. Okay, into 1K. So GM1 let cancel. Okay, and also I know GM1 is equal to GM2. So is equal to minus Vs into 1K divided by 1 by GM1 plus 1 by GM2 is equal to 2 by GM1, because GM1 is equal to GM2 already we have seen. Okay, so is equal to minus GM1 by 2 into 1K into Vs. Okay, so the simplest voltage gain is V0 by Vs is equal to minus GM1 by 2 into resistance 1K. What is GM1? GM1 is minus IC by Vt into 2 into 1K. What is IC? IC is nothing but minus IC is 2 milliampere. 2 milliampere divided by Vt is given 26 millivolt. 26 millivolt into 2 into 1K. Okay, so do the calculation. You can get the answer. Is equal to 2 into 1000 divided by 26 into 2. So how much I got? Is equal to 2 milliampere by 2 milliampere got cancelled. Okay, so it will 2 by 2 got cancelled. So 1000 by 26. So 1026 is 38.4. So I got 38.4. Just a minute. I think some calculation mistake is there. So there is a mistake. Right? This is 2.6 milliampere, right? Not 2 milliampere. You can see this is IC is nothing but 2.6 milliampere. I put 2 milliampere. So you have to put 2.6 milliampere, right? So if you put 2.6 milliampere, okay, 2 show 2.6 get cancelled. So milli get cancelled. 10 by this is 10 will cancel. So I'll get is equal to minus 50. Okay, so the answer should be minus 50. Minus 50. So minus 50. If somebody would have practiced a lot, could get the answer in 2 seconds. But if you don't have practice, then you have to first find out the resistance looking to the emitter, then put the T model. If you put the T model, I can easily calculate the output voltage because of the input source Vs. Okay, let's see the next question. So next question is in the voltage reference circuit. Okay, what is a voltage reference? Reference means a circuit which gives a output voltage which is almost constant across the temperature variation, process variation, and input supply variation. It's a reference, means it's constant voltage. Okay. What is a voltage reference? A voltage reference is giving a voltage who should be constant across. Constant means a very less variation. Okay. So the voltage reference output should be having very less variation across temperature variation, process variation, and also the supply variation. Right. Shown in the figure. The op-amp is ideal, right? The transistor Q2 to Q13 are identical and in all aspects. Okay. So transistor Q1 to Q32. So Q1 to Q32 all are same transistor. Okay. Having infinity large values of common emitter current gain beta, means since beta is very high, I can say the collector current is equal to the emitter current. When beta is very high, so IB is negligible. IB is negligible. Okay. The collector current IC of the transistor is linked to base emitter voltage by the equation IC is equal to IS into exponential of VB by VT, that you all of know. IS is the reverse saturation current. Assume that VP is 0.7 volt and VTH is 26 millivolt. Calculate the output voltage, right? So in this circuit, you have to find out the output voltage V out. Okay. This is a very interesting and beautiful question. Okay. Let us see how to solve it. Okay. So what are the things we know? Okay. First thing is, in any circuit, right? Whenever you see a new circuit, whatever you know, you just put that information. Then you will get a way to find the answer. Okay. Always the trick is, whichever things you know about whatever things, okay, you just dump into the one board. Then you will see how to get the final answer, how to get a link between different constraints. Okay. So the first thing is, since this transistor op-amp is operating in negative feedback, because some part of my output is connected to my input. Okay. So I can say it is obeying a principle called virtual ground. That means the voltage at the negative terminal is equal to voltage at the positive terminal. Okay. This is the first thing. Another thing is what? Since V negative is equal to V positive, okay, and if you see the resistor 20K, right, both are connected to output, and the other end is V positive, another end is V negative. Since both are same potential because of virtual ground, so the current in 20K of the left is equal to current of 20K of the right. Since this potential is connected to V output, and since V plus is equal to V minus because of virtual ground, so voltage across 20K is same. So I can say current here is equal to current here. So current in this branch is equal to current in this branch, right? So this branch current is, I can say I1, right? This branch current is, I can say I2. This is I2, right? Because okay, this current is I2. Since it is ideal op-amp, no current will flow through the negative terminal. All of I2 will come to 5K, and this is I2. Okay, and similarly, this is I1. All of I1 will come to this transistor collector Q1. Okay, so IC1 is equal to I1, right? Now this I2 is coming, right? And this I2 is nothing but is equal to I1 only, right? This is one thing you know. Another thing you know is, since the transistor Q2, Q3, Q32, right, is in parallel, right? Transistor Q2 to Q33, 32 is in parallel. So the current whatever is coming, right, all the current divide equally between all transistor, right? So I can say so the current I2 is coming, I2 is nothing but I1, and since all are connected in parallel, having same base to emitter voltage, and all are identical, so the I2 will divide equally between these two, right? So this will be equal to how much, guys? You see, this will be I2 will go to collector of Q2 to collector of 32. So I can say IC2 is the current collector current of transistor 2 is equal to IC3 is equal to up to, it will go up to IC32 is equal to my input current divide equally. So my input current is I2 is nothing but I1 only. Okay, divide by how much transistors are there? Q2 to Q32 is nothing but 31, right? Number 31. So this is 31. Clear? Because the I1 coming dividing between all the transistor. So the collector current of each one is nothing but I1 divided by number of transistors is nothing but 31. Q2 to Q32 is 32 minus 2 is Q2 to Q2 Q3 8. Then what is how much? Q2 to Q32 which is equal to 31 only, right? 31. So now we know IC2 IC this is equal to I1 by 31. Okay, so next thing is, these things you already know from the given circuit. Okay, now what is the current of 5K? Okay, current flowing to the 5K is so this is VB1, right? This is VB1. So 5K is positive terminal is at VB1, right? Since because of virtual ground, V positive is equal to V negative. V positive is equal to V negative is equal to, what is V positive? V positive nothing but VB1 is equal to VB1, right? VB1. So what is the voltage across 5K is nothing but V positive is equal to V negative VB1 minus VB2. This is VB2 right? So voltage across 5K is VB1 minus VB2 divided by 5K, correct? So let us see what is the current in 5K. Since this is VB1, because of virtual ground, V positive is equal to V negative is equal to VB1 here, VB1. Okay, and another end is connected to VB2. This is VB2, and the current flowing through is IC2 is nothing but I1 by 31, right? Already you told this and 31. Now, what is the current in 5K is VB1 minus VB2 divided by 5K. Okay, so what is this? What is VB1? We know VB1 is nothing but, since IC is equal to IS into exponential of VB by VT. So since we know IC1 is equal to IS exponential of VB1 by VT. So what is VB1? VB1 will be equal to VT ln IC1 by IS. Similarly, what is VB2? VB2 is equal to IC2 is equal to, okay, is equal to IS exponential of VB2 by VT, right? So what is IS? What is VB2? If you take ln, it will be equal to VT ln IC2 divided by IS. Why I have the same as, since the transistors are exactly identical, so the reverse saturation current should be same, because all are exactly identical given, right? All are exactly identical. Q1 to Q32 is identical. That's why I put Is same for both the current. Okay, so by 5K. So this implies Vt into ln IC1 by Is minus IC2 by Is, so is equal to IC1 by Is by IC2 by Is is equal to IC2, right, by 5K. Okay, so Vt ln IC1 is nothing but I1, right, I1 divided by IC2 is nothing but I1 by 31, right, divided by 5K is equal to Vt ln 31 divided by 5K. Okay, this is the current of 5 kilo ohm resistor. Okay, so the same current will flow through the 20K also. Okay, so now what is the output voltage? Now it is very easy, right? Output voltage getting is very easy, right? Now my output voltage will be equal to, you see, current in 5K is nothing but I1 is equal to Vt ln 31 by 5K. So what is the output voltage now? So my output voltage will be, the output is equal to, I know the current here is I1, here also the current is I1, here also the current is I1, okay, is equal to V0 equal to I1 into, so let's put the, okay, so this is nothing but I1, okay, I1, okay, and I1 is nothing but I5K, because the same current I1 is flowing through 5K, so is equal to I5K, nothing but I1, this is equal to I1 only, right, because the current through 5K is nothing but my I1 only. So let us put a nodal equation here, KVL here. Okay, so V out minus I1 into 20K minus I1 into 5K minus Vp is equal to 0, right? I put nodal equation here. Okay, V0 minus I1 into 20K minus I1 into 5K minus Vp is equal to 0. Simplest V out is equal to I1 into 20K plus 5K is 25K plus Vp. What is I1? I1 is given Vt ln 31 by 5K. So it is equal to Vt ln 31 by 5K into 25K plus what is Vp? Vp is given already 0.7 volt, right? 0.7 volt. So this is equal to to calculate 26 millivolt into ln 31 into 5 into 5 plus 0.7. So 0.7 plus 26 milli minus 3, 26 milli into 5 into ln 31. So I got equal to 1.146 volt. Okay, so the output is 1.146 volt. So it is called a voltage reference. And you could see the output here is not depending upon my supply voltage 15 volt minus 15 volt. It is, you see the output equation. In the output equation, output depend upon only 25K and 5K, the ratio between 5K and 20K, right? The ratio between the two resistor and the VB, right? But it is not depending upon my supplies. Okay, so output is independent of supply variation. Okay, and if you do a little bit of insight into this, you see it will be a sum of two output to make the output constant at 1.146 volt. Okay, so this is called a voltage reference. So I think that's all. Thank you guys.